Hello, everyone. My name is Randy Kolka. I'm a research soil scientist with the Northern Research Station, arm of the Forest Service in Grand Rapids, Minnesota. And I'm going to talk about one of the neatest experiments on the planet today, the spruce and peatland responses in our changing environments experiment here in northern Minnesota. Just about by any metric a person can think of as far as number of folks involved, economic impact to the local economy, number of publications, especially high-profile publications. Spruce is the largest, most expansive climate change experiment on the planet. And that's not just in the peatland wetlands that I'll talk about in a little bit, but any ecosystem on the planet. And spruce is really an experiment to look at these high-carbon northern peatland ecosystems to whole increases in temperature, that's both above ground and below ground, and elevated carbon dioxide. It's funded by the Department of Energy, and it's really a cooperative partnership between Oak Ridge National Laboratory in Tennessee and us, with hundreds of collaborators and students within the US and across the globe. So I study these peatland ecosystems. Well, at one point they were kind of understudied, just like permafrost and Arctic regions, but because of their importance on climate change, they're getting their day. They have the potential to show dramatic carbon cycle shifts in organism responses under what's going on with our climate. And in this case, we're at the southern boreal extent, which would make these ecosystems here, the peatlands, the bogs, a little vulnerable to climate change. They have historically and continue to be important greenhouse gas feedbacks to the atmosphere, both carbon dioxide and methane. But how is warming going to influence that? That's the question for spruce. And the real reason why spruce is here is to provide data to enhance our global circulation models. Unfortunately, up to this point in time, wetlands, in particular peatlands, are not very well represented in our global circulations model for the planet. And hopefully, if we start including some of that important wetland information, we can predict our future climate a lot better. As we all sort of know, I think we're expected to see the highest temperature changes with higher latitudes in this part of the world. And here in northern Minnesota, we're in a pretty bright red zone there in the upper right. The spruce bog is down to the right there. And it's about 20 acres or 8 hectares. And the depth profile shows that in that bottom left-hand corner that the peat is about 9 meters deep, or about 30 feet deep. So there's tons and tons and tons of carbon stored in our ecosystems here in northern Minnesota, across the boreal region of Canada and the US, across northern Europe, and across Russia and other places. To the extent that these peatlands only represent 3% of the terrestrial area of the planet, but they house 30% of the carbon on the planet in terrestrial zones. So really making them disproportionately important from a carbon storage point of view. And if we start to increase these ecosystems to be less storage devices and more or sinks, basically carbon sinks to be in sources as a result of warming, we could be looking at exacerbating climate change in the future. So if you look at this one peatland, the spruce peatland, and there's thousands of these just in Minnesota, the amount of carbon that's stored there in that peatland is about the same as about 260,000 flights from Duluth, Minnesota to Minneapolis, St. Paul, to give some context to how much carbon is actually out there in just one little peatland. In the spruce experiment, we have 5 different temperature treatments and 2 different levels of carbon dioxide. Our warming treatments range from 0 to 9 degrees centigrade, and that's always a differential from outside. So today in northern Minnesota, for example, our temperature is about 35 degrees centigrade. So in the chamber, it would be 44 in the warmest chamber. Elevated carbon dioxide, which is a sort of a plant fertilizer. We're breathing in about 410 right now. The elevated carbon dioxide chambers have about 900 part per million, which is about twice our current levels, but consistent with the year 2100 projections. So we have 5 temperature controls, 5 temperature treatments, 2 different levels of carbon dioxide. So 5 times 2 equals 10 chambers. And we also have unchambered controls to test the effect of the chambers themselves on the ecosystem. It's impossible to put a chamber around an ecosystem both above and below ground and not have any effect on them. And we have unchambered controls to assess that. Here's a little cartoon. They're open topped, about 12 meters in diameter, about 8 meters tall. The real novel aspect of spruce, though, is the deep soil heating down to about 6.5 or 7 feet in the peat. And basically, we took like the filament of your 100-watt light bulb, and we made it long, and we stuck it in a steel pipe and added electricity, and it creates a certain aura around that pipe of heat. You put those pipes in a certain geometry, and that's concentric circles from the middle. You can heat as far and wide as you want. Again, no one's ever done that before, and that's one of the most novel aspects of spruce is the below ground heating. We also have a below ground environment enclosed with a subsurface chamber, as you can see there, to basically isolate the hydrology, so we can look at chamber level fluxes in and out, both in the air and in the atmosphere, but also in the water leaving the chamber. This is our experimental design, theoretical. On the y-axis is some response. It can be anything you can think of. We're measuring hundreds of things. And then on the x-axis is the temperature differential. And you can imagine, let's just say that black spruce growth, let's say black spruce like elevated temperature to some degree, and they get bigger and better over time. And they might even like it better with elevated carbon dioxide, the red circles. But at some point, it just gets too hot. Black spruce doesn't exist in these environments, and they start to go downhill. That would explain that response. Like I said, these responses can look like anything you can think of. And it's those responses that we're accumulating that will feed into these global models to predict our future climate. So we're in, again, northern Minnesota at the Marcel Experimental Forest, USDA Forest Service Marcel Experimental Forest. We're north of Grand Rapids on the Chippewa National Forest. And you can see we're a mix of different upland, bogs, fens, lakes, and streams. And the experimental experimental forest is actually named for the Marcel moraine, which was a glacial feature in the landscape. And at Marcel, we've been studying peatlands since about 1960. First, to just understand what they were, their soils and ecology and hydrology. Then we did a bunch of management experiments over time to look at the effect of harvesting and burning and other things on peatland watersheds. And then the acid rain days hit, so we started really looking at sulfate and nitrate deposition and cycling. About 1990, we really were interested in developing a research program around mercury. That's a story for another day, but these ecosystems are really important sources of the bioaccumulative form of mercury, the methyl mercury. And about that same time, we were already starting to see climate change in our part of the world. And if you look at the graph on the bottom right, for example, we went up a little over 2 degrees Fahrenheit, or about a 1/4 degree Celsius every 10 years for the last 60 years. So you can debate on why warming is occurring, but there's really no debate at this point that it is occurring. To the point where we got starting to lose some of our institutional knowledge, and we wrote a Bible on the Marcel Experimental Forest in about 2010, came out in 2011. So we have the history preserved and all the results preserved in this book, and we'll do that periodically over the next however long we're here. So this is spruce, overhead of spruce. I had a 4th grade class up couple of years ago, just pre-COVID, and I asked what it looked like from above before we went to visit it. And little girl raised her hand. She said, "It looks like spaceships have landed. They planted little spaceship eggs, and now the spaceship eggs are just starting to come out of the ground." So I think that's pretty accurate. It's pretty sci-fi out there. It's pretty neat. Here's an overhead looking straight down on one of the chambers. And I'm not going to talk about this at all, but suffice to say, if you're going to put in all this infrastructure, you're going to try to measure everything you can think of. So we indeed do that. All this discussion started in 2009 when the Department of Energy was looking for their next big science experiment. And we went through a lot of protocols and whatnot, and we began the different phases of warming at first, below ground, above ground, and then we added the elevated carbon dioxide in 2016. And we'll run the experiment through the calendar year, or at least the field season of 2025. And 2026, we'll start decommissioning the experiment. So a few interesting results. We are definitely warming these ecosystems to the point where we are dramatically increasing methane emissions and also carbon dioxide emissions. The methane emission part's really important because methane has a lot higher ability to trap greenhouse gases than carbon dioxide does. They're a much bigger greenhouse gas, more important, even though they're at much smaller concentrations. So, and these ecosystems are notorious sources for methane, but we are definitely cranking up the methane coming out of these ecosystems. The deep soil warming, we were interested to see if the deep soil warming was leading to decomposition of the peat that's been buried for thousands and thousands of years. And if you look at the graph, the first graph on the left, the furthest left line is actually the soil age. And if you go down to the very bottom there in the carbon-14 scale, on that one point, it's about 10,500 to 11,000 years old. The points on the right there are all the ages of the pore water concentrations of carbon, which lead to the emissions. And then ultimately the emissions coming out of the soil as well, and that age of the carbon in those emissions. And at first it was all relatively new. We seemed to be just recycling carbon a lot faster, but we weren't getting into that, centuries and thousands of year old carbon that had been stored there basically. And now we resampled again not too long ago, same experiment. And you can see on the right there, the right group in the one column with mostly the blues there is from the previous experiment. And the reds are coming later in the experiment now. And as you can see, the reds are starting to move towards that line of the soil in the other graph. And so we are starting to mine that carbon that has been buried there for thousands of years. And that's not good. That carbon should stay there forever. So we're actually starting to mine the carbon, not just cycling it faster. There certainly appears to be a response to warming on decomposition. This is a standard material. We have a bunch of decomposition studies going on out there, the rate at which things decompose, like needles and sphagnum and wood and branches and a number of things, different roots, etc. And the more decomposed something gets in this circumstance, the lower the tensile strength. The tensile strength is the amount of force it takes to pull apart these cotton strips after they've been in the ground for a while. And as it gets lower, they're more decomposed. And as you can see, all the hot colors have very low tensile strength. So a lot more decomposition occurring in the warmest treatments. If you add it all together like you would in your checkbook, and you put in all the gains and all the losses, or all the income versus all the expenses, as you can see at the warmest temperature treatments, we really are losing a lot of carbon. much more than we probably anticipated at the very beginning. And we have certainly flipped these ecosystems that were warming to what have been carbon sinks for thousands of years to being carbon sources to the atmosphere. And as you can see, that line there is sort of the zero gain line, zero loss line. And even at the modest temperatures to the left in that graph, we are still at a negative net carbon exchange. So the checkbook is negative, even at moderate amounts of warming. To the extent that if you measure the elevation out there in the warmest treatments, we've lost about 10 centimeters or about 2.5 inches of elevation in the warmest treatments. And we didn't expect that at all, that we could actually see changes in elevation. But we have, and it's amazing that that amount of carbon has been blown off just in the 5 years or so, 6 years that we've been warming. And it takes probably 500 to 1,000 years to accumulate that 10 centimeters. And we just blew it off in a series of a few years with the temperature treatment. So impressive, but not good. As far as the plants go, some are winning, some are losing. The trees are definitely losing. That's the graph on the left. Black spruce growth rate is decreasing over time, and the triangles are the tamarack. They also are decreasing over time. The community that is taking advantage of the warming conditions to the greatest extent is the shrub community. And it's low ericaceous shrubs like blueberry and Labrador tea and others have really exploded out there in the warmest chambers. And so if you're looking to have more blueberries in the future, we're definitely going to have more blueberries in the future with warming in these ecosystems. It's going to be a blueberry world. The problem with the shrubs exploding is they're shading out the most important plant that's out there, and that's the sphagnum moss. And the graph on the left, you can see the sphagnum moss decrease in production, that primary production with warming. It's the sphagnum moss that's the building block and the reason why all that carbon is out there since glaciation. So it's the smallest plant in the ecosystem, is really the most important plant of the ecosystem. It's not the shrubs, it's not the trees. It's the sphagnum moss that has been the main contributor to building up these carbon storage in the spots in the landscape since glaciation. We're also dramatically decreasing lichen growth on the trees with warming. Part of the reason why the shrubs are winning is they have considerably more fine root growth with increasing temperature. And trees have shown not to. And so the shrubs are able to explore more area and get more resources. And that appears to be a huge advantage with warming. As far as the phenology, or when they, in this case, phenology we're talking about is when they green up in the spring and green down in the fall. And I won't get into the figures. But if you get into the figures, the growing seasons increased about 10 weeks for the shrubs, but only about 4 to 5 weeks for the trees in the warmest chamber. And so again, the shrubs are getting a longer growing season than the trees as a result of warming. They're greening up earlier in the spring and greening down later in the fall, basically, than the trees. And finally, the last reason why we think the trees are losing is that we have these occurrences in this part of the world of false springs. And so when we get a day, and I'm going to use Fahrenheit in this case, when we get a day in, let's say, March, where we get to be 45 degrees Fahrenheit, the ecosystem responds like it's spring. The trees start putting on needles, start putting out roots and cones and whatnot. But then 2 weeks later, we can get a minus 10 degree series of days, and they get frostbite and they have to drop everything and start over again. We have always had fall springs, we'll always will have fall springs, but because of the warming treatment, the frequency of these fall springs is increasing there more than the lower warm treatments. And so when you get too many fall springs, the trees use the resources they have And then if they have to do it over again and over again and over again and over again, they run out of resources and they are not viable at that point. And again, the shrubs don't appear to be susceptible to this. So thank you very much. Let me know if you have any questions.